What happens when a comet seems to be alive? 3. I divided by Atlas, a traveler from another star system, is exhaling 40 kilograms of water vapor every second into the cold void. It's too far from the sun to be doing that. Astronomers are whispering, it's acting alive. But its mystery doesn't end there. Strange nickel without iron, cyanide in its tail, and whispers of an origin billions of years older than our own solar system. Meanwhile, far from this interstellar visitor, citizen scientists stumble upon the largest odd radio circles, ORS, ever discovered. Mercury and Ceres align strangely in the October sky, raising questions about a possible link with 3I divided by Atlas, and Blue Origin's October flight. It raises more questions than answers. Did it even happen? Stay with me until the very end as we confront these unsettling questions in our first new multi-story format to keep our late-night listeners up to speed with all the cosmic news happening in our skies. If these mysteries have you hooked like they have me, make sure to hit like and subscribe so you don't miss a single update as this unfolds. Leave a comment letting me know where you're tuning in from, what time it is there, and whether you believe we're being told the whole truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You are the reason we can keep chasing stories like this. Thank you for having our back. Imagine this. You're floating in the cold silence of space, more than 3 times farther from the sun than Earth is. Out here, sunlight is just a whisper. Ice stays frozen. Comets are dormant. Everything sleeps. And then you see it. A comet hemorrhaging water into the void, pouring 40 kilograms of the stuff into space every second. Not a trickle, a flood. Water gushing from a frozen rock where water has no business flowing at all. This is 3I divided by Atlas, an interstellar comet that arrived in our solar system from somewhere else, carrying rules from another star's backyard. And those rules, they don't match ours. The first clue came from SWIFT, a space telescope designed to hunt gamma-ray bursts. SWIFT saw the impossible, a halo of hydroxyl, OH, molecules surrounding the comet. Hydroxyl is what you get when sunlight rips water molecules apart. It's the echo of water screaming as it dies. When you see OH, you know water was just there. And SWIFT saw a lot of it. The numbers are staggering. 3I divided by Atlas was releasing 40 kilograms of water every second. For context, that's like dumping a small car's worth of water into space every minute, at a distance where our comets are nearly silent. Our solar system's comets don't do this. Not out here. They're cold, dormant, practically dead. Water ice needs heat to sublimate, to turn directly from solid to gas. And there just isn't enough solar energy this far out. 3I divided by Atlas didn't get the memo. You might remember Oumuamua, the first interstellar visitor. It was dry, as a bone, no water, silent. Then came 2I divided by Borisov. Borisov was active, sure, but it behaved exactly like our comets. It followed the script. It was boring in the best possible way. 3I divided by Atlas is neither of those things. It's alive, in a way that shouldn't be possible. It's screaming water into the space where silence should be, and the question hanging over every astronomer is, how? What mechanism could be driving this? Is there some exotic ice we don't know about? Or is there some chemical reaction happening inside that rock that we've never encountered before? Water is just the beginning. Comets are supposed to follow certain rules. When they get hot enough, metals start to vaporize. Iron and nickel appear together, like old friends who always travel together. You see one, you see the other. It's a cosmic constant we rely on. Except 3I divided by Atlas didn't read the textbook. The Very Large Telescope, VLT, in Chile aimed at 3I divided by Atlas and found something absurd. Nickel emission lines were blazing bright in the spectrum. Strong, unmistakable, impossible to ignore. And iron? Either absent or so weak it barely registered. Nickel without iron. It's like finding smoke without fire. Like finding footprints without feet. In our solar system, this doesn't happen. Iron and nickel sublimate at similar temperatures. They are chemically bound together. But 3I divided by Atlas was apparently formed somewhere that plays by different rules. Several explanations have been offered, and none are simple. One possibility is chemical fractionation. Maybe where 3I divided by Atlas formed, nickel hitched a ride with volatile compounds, while iron got locked into solid minerals that need much higher temperatures to vaporize. Or perhaps, and this is the most exciting possibility, 3I divided by Atlas comes from a stellar system with genuinely different elemental abundances. Not all stars have the same chemical recipe. Maybe its parent star was chemically odd, and that oddity is now written into every molecule of this comet. We have to be careful. Maybe iron is there, just below the detection limit. But what if it never shows up? That would be revolutionary. It would tell us that planetary systems can create comets with metal chemistry so different from ours that our models need to be completely rewritten. This is why astronomers are watching 3I divided by Atlas obsessively. Every observation is a test. Every spectrum is a chance to confirm our understanding or shatter it. And right now, 3I divided by Atlas is doing more shattering than confirming. Comets are supposed to brighten gradually as they approach the Sunday. The physics is simple. More light, more heat, more gas and dust. The relationship should be smooth, predictable. 3I divided by Atlas apparently didn't get that memo either. Observers noticed something strange about its color. At first it was neutral, slightly reddish, but as it got closer, it started turning green. Not a subtle shift, a vivid, eerie, unmistakable green. That green comes from two sources: cyanide molecules and atomic nickel. Both glow strongly in the green part of the spectrum, and both started ramping up dramatically as the comet warmed. The brightness increase wasn't linear, it was superlinear. It was brightening faster than basic physics predicted. Something was being unlocked. A new process was kicking in. Astronomers call this switch-on behavior. Imagine a temperature threshold. Below it, a specific ice stays solid, locked away, dormant. Then the comet crosses that threshold, and suddenly, that ice begins to sublimate. Gas production spikes. Like flipping a switch. One moment it's off, the next it's on. 3I divided by Atlas seems to have multiple switches. Water turned on first, at an impossibly far distance, which was already anomalous. Then came the cyanide and nickel, blazing green as the comet warmed further. Each emission suggests a different volatile reservoir being tapped, a different chemical environment reaching its activation threshold. Or perhaps the comet is cracking itself open as it heats, revealing layer after layer of frozen chemistry. This isn't a stable, predictable comet. This is a drama unfolding in real time. Every object in space carries a story written in its trajectory. Where it's going tells you where it's been. And the trajectory of 3I divided by Atlas is telling a story that spans billions of years and thousands of light years. Its orbit is hyperbolic. That's the technical term for an open curve, a path that doesn't loop back. 3I divided by Atlas came from interstellar space, swung past the sun, and will leave, never to return. Astronomers tracked its path backward, stitching together old observations, and that trajectory points outward, back into the galaxy. But not just anywhere. Orbital models, combined with data from the Gaia telescope, which has mapped the positions and motions of billions of stars, allow astronomers to make educated guesses about where 3I divided by Atlas might have originated. The answer is surprising. The galaxy has structure. Most stars, including our Sun, live in the thin disk of the galaxy. But there's also a thick disk, a population of older stars, formed earlier in the galaxy's history. They are chemically different. The trajectory of 3I divided by Atlas suggests it might have come from the thick disk. If that's true, if this comet was formed in that ancient population, then it could be older than our solar system. Our solar system is 4.6 billion years old. Thick disk stars can be 7 billion years old or more. That means 3I divided by Atlas could be carrying ice and rock from a time before the Sun even existed. Think about the chemical implications. The gas cloud that formed that star 7 billion years ago had fewer heavy elements than the cloud that formed our Sunday. Maybe that's why we're seeing such a high carbon dioxide to water ratio. Maybe that's why the metal ratios look weird. Maybe this comet is a chemical fossil from a time when the galaxy was younger. We can't be sure. But the fact that it's possible is extraordinary. We might be looking at a relic, a time capsule from the ancient galaxy. Comets are cargo ships, carrying the molecular inventory of their birth environment. And 3I divided by Atlas is carrying some very strange cargo. We've talked about the water, but carbon dioxide is the real shock. Observations suggest 3I divided by Atlas has an extraordinarily high carbon dioxide to water ratio. In our comets, water dominates. It's the primary driver of activity. 3I divided by Atlas reverses that script. Some measurements suggest 95% of the volatile emissions are carbon dioxide, with water as the minority component. That's backward. It's inverted. It's nothing like what we see at home. Why would a comet be so rich in carbon dioxide? Maybe its formation temperature. Or perhaps the giant planets in that system migrated differently, stirring up the disk and mixing materials in unexpected ways. And then there's the cyanide. Cyanide appeared after the water, later in the warming sequence. In our comets, they tend to appear at the same time. This delayed appearance suggests it might be trapped differently. And of course, there's the nickel, glowing green, separated from its iron companion. Now, let's talk about the elephant in the room, the panspermia hypothesis. The idea that life, or at least the building blocks of life, can spread through space on comets. 3I divided by Atlas has water, organics, and cyanide, a key precursor in prebiotic chemistry. If you wanted to design a comet to seed a planet with interesting chemistry, you would include exactly these ingredients. But let's be clear. This is speculation. There is no evidence 3I divided by Atlas is carrying life. There is no evidence any comet has ever carried life. Cosmic radiation is brutal. Over millions of years, it rips complex molecules apart. DNA, proteins, even simple amino acids can be destroyed. But complex molecules could survive. Not living things, but chemical fossils. Molecules synthesized in its parent star system, perhaps in a planet's atmosphere, and then incorporated into the comet. They could survive the journey. And if we could analyze them, they could reveal the atmospheric chemistry from an alien world. They could be messages written in carbon and nitrogen, waiting for someone to decode them. This is why some scientists dream of intercepting one of these interstellar visitors, not just observing it from Earth, but sending a spacecraft to it, landing on it, drilling into it, and analyzing the samples. The technological challenges are immense. 3I divided by Atlas is already too far away. We didn't catch it this time, but it's showing us what's possible. It's showing us what's out there, and it's making us hunger for more. Sometimes, the most important discoveries happen just because someone looked at the data in the right way. Not with algorithms, not with machine learning, but with human eyes and human intuition. And sometimes, that someone isn't a professional astronomer at all. Let me tell you about odd radio circles, ORCs. If you've never heard of them, you're not alone. They were only discovered in 2019, which is practically brand new in astronomy. ORCs are vast circular structures, visible only in radio wavelengths. You can't see them in optical light. You can't see them in infrared. But point a radio telescope at the right patch of sky, and there they are. Perfect rings of radio emission, sometimes hundreds of thousands of light years across, floating in space like cosmic smoke rings. No one knows what they are. They're truly mysterious, and finding them is hard because they're faint. Automated detection algorithms tend to miss them because they're trained to find point sources or compact objects, not giant, diffuse rings. And this is where radio at home comes in. It's a citizen science project where volunteers visually inspect radio maps, looking for things that don't fit. They're not looking for anything specific. They're looking for weirdness. And in March 2025, a volunteer flagged something extraordinary: a pair of intersecting radio rings, twin circles overlapping in the sky, creating a figure-8 pattern. It's the most distant and powerful ORC discovered to date, and it was found not by an algorithm, not by a professional survey, but by someone volunteering their time to stare at data. The discovery was made using maps from LOFAR, a radio telescope network spread across Europe. LOFAR generates an enormous amount of data, too much for professional astronomers to examine by hand. Automated pipelines process most of it, but those pipelines have filters. They're designed to catch the expected, not the unexpected. This is where human pattern recognition becomes invaluable. Our brains are incredible at spotting things that don't belong. The volunteer who found that ring didn't need to know the physics of ORCs. They just needed to look at the image and think, "That's weird." And they were right. But it's not just that one object. Radio at home has flagged multiple anomalies. Another volunteer found a giant radio galaxy with a peculiar ring structure. Another found a ring at the end of a jet, a feature that theoretical models didn't predict. These are objects that would have been lost in the data flood if humans hadn't been looking. There's a lesson here that extends beyond radio astronomy. We're entering an era of the data deluge. The Vera Rubin Observatory, when it comes online, will generate 15 terabytes of data every night. No human team can look at all of that. No set of algorithms can catch every anomaly. We need both. We need machines to handle the bulk processing and humans to catch the weird edge cases that don't fit any template. Now, let's connect this back to 3I divided by Atlas. Could a citizen scientist have flagged its anomalies early? Could someone looking at the spectral data have noticed the nickel without iron signal before professional astronomers did? Could someone monitoring comet activity have said, "Wait, why is this thing active so far from the sun?" Maybe, maybe not. But the point is, anomalies like 3I divided by Atlas benefit from having as many eyes as possible on the data. Professional astronomers have expertise, but they also have expectations, models they are trying to confirm. Amateurs and citizen scientists bring fresh eyes. They aren't constrained by what should happen. They're free to see what is happening. In the future, as telescopes flood us with petabytes of data, citizen scientists might become the first responders to cosmic oddities. They might be the ones who flag the next interstellar comet, the next weird radio structure, the next thing that doesn't make sense. And when they do, professional astronomers will follow up. It's a partnership, and like all good partnerships, it's stronger than either component alone. But let's not pretend this is all sunshine and collaboration. There's tension here, real tension. Because opening the gates to citizen science means dealing with false positives, with well-meaning amateurs who flag things that turn out to be noise, with conspiracy theorists who see alien signals in every data glitch, and professional astronomers, understandably, worry about this. A discovery isn't a discovery until it's been verified and peer-reviewed. That takes time and expertise. False positives are a real problem. Someone flags an object as unusual. Astronomers spend weeks following up, only to determine it's instrumental noise or a satellite trail. That's time that could have been spent on genuine discoveries. Then there's confirmation bias. When people are looking for something specific, they tend to find it even when it's not there. This happens to professionals too. but training and peer review provide checks. But the thing is, these challenges aren't insurmountable. Training protocols can help. If citizen scientists are taught how to recognize artifacts, the false positive rate drops. The opportunities are enormous. Crowdsourcing anomaly hunts means you can search larger datasets more thoroughly. Let's bring this back to 3I divided by Atlas. Could a citizen astronomer have flagged its nickel anomaly early? The spectral data is public. Anyone with the right software can download it and look. But spectroscopy is hard. It requires understanding. But maybe with training, with guidance, with a community, someone could have noticed the oddity before it made headlines. The same goes for the water production rate. Comet light curves, measurements of brightness over time, are often contributed by amateur astronomers. If they had been trained to recognize unusual activity patterns, they might have flagged 3I divided by Atlas's superlinear brightening. Past citizen-led discoveries prove this works. The Planet Hunters project has discovered multiple confirmed exoplanets. Amateur asteroid hunters have found near-Earth objects that professional surveys missed. The conclusion isn't that we should replace professional astronomers with amateurs. That's absurd. The conclusion is that we need both. We need professionals for the deep expertise, and we need citizen scientists for the breadth of coverage, the fresh perspectives, and the sheer number of eyes. It's not a competition. It's a partnership. And in the era of the data deluge, it's a necessary partnership. October 2025 brought something unusual. Excellent viewing conditions for both Mercury and Ceres. On social media, people started connecting the dots. Mercury is visible, Ceres is visible, and now this weird interstellar comet, 3I divided by Atlas, is acting alive. Are they related? Is there some cosmic alignment happening? Are the solar system's gravitational fields triggering the comet's activity? Let's be clear. No, there is no connection. Mercury's orbit has nothing to do with an interstellar comet outgassing. Ceres's position has no influence on chemistry happening billions of miles away. These are independent events, coincidentally happening at the same time. But humans love patterns. We are hardwired to find them. It's a survival trait. And sometimes it goes into overdrive. This is pareidolia on a cosmic scale. Pareidolia is seeing faces in clouds, hearing voices in static. It's pattern detection gone haywire. 1910 provides a perfect historical analogy. That's the year Halley's Comet returned, and people were terrified. Astronomers had detected cyanogen, a toxic gas, in its tail. Newspapers ran sensational headlines. Comet's poisonous tail will pass over Earth. People bought gas masks. Some even committed suicide. Of course, nothing happened. The comet's tail is incredibly diffuse. The amount of cyanogen that actually reached Earth was negligible. We're seeing the same thing now, with 3I divided by Atlas. The comet is weird, genuinely anomalous. Mercury and Ceres happen to be visible at the same time, and suddenly people are constructing narratives. Astronomers have run the numbers. The gravitational influence of Mercury on an object in the outer solar system is essentially zero. But facts don't always matter when the narratives are compelling. The human brain craves stories. We want events to be connected, because unconnected events feel random, chaotic. If they're unrelated, then we live in a universe where strange things just happen, and that's psychologically uncomfortable. Social media amplifies this exponentially. A conspiracy theory gets posted, and it instantly finds a community of like-minded people. The lesson here isn't that people are stupid. The lesson is that coincidences are powerful, and our brains aren't well calibrated to dismiss them. This matters because it affects how people interpret anomalies like 3I divided by Atlas. If you're primed to see cosmic conspiracies, then the comet's weird behavior becomes evidence of something larger. And that brings us to an even weirder chapter in this story, the 8th of October 2025. Blue Origin mission NS-36. 6 passengers, 11 minutes. One mystery flyer whose name was kept secret until landing. The capsule launched, crossed the Kármán line, floated in microgravity, and touched down in the Texas desert. Success. Another flawless flight for the company's space tourism program. That's the official story. A few news outlets covered it. A few space journalists tweeted about it. Almost normal. But here's the weird part. Here's the thing that keeps nagging at anyone who follows spaceflight closely. The silence. The eerie, almost suffocating lack of coverage. No viral videos, no trending hashtags, no celebrity reactions or memes. A spaceflight, something that just a few years ago would have been headline news for days, barely registered a blip. Think about that for a moment. 6 human beings left the planet. They experienced weightlessness, saw the curve of the Earth, and returned safely. That should be extraordinary. But the internet shrugged. The story vanished like smoke. Why? Why so little documentation? Blue Origin usually releases beautiful in-cabin footage. Where was it? Why wasn't it splashed across every news site? Why did the mystery passengers revealed generate no curiosity? Radio silence. It's as if the flight happened in a vacuum, not just the vacuum of space, but a vacuum of public attention. And that vacuum, that absence, starts to feel like its own kind of presence. The silence becomes louder than any announcement. You start to wonder, did this flight really happen as described? Was it 6 passengers? Was the mystery passenger real? Did the capsule actually launch on October 8th? Or was that footage from a previous flight repackaged with a new date? These are paranoid thoughts, conspiracy thinking. But sometimes, the absence of evidence feels significant. When something should make noise and doesn't, you have to ask why. Now, let's contrast this with April 2025. Just 6 months earlier, Blue Origin launched another New Shepard mission, and that one exploded into public consciousness. Not because of a malfunction, because of who was on board. Katy Perry, Gayle King, an all-female crew, high-profile passengers. And it did generate headlines, but not the ones Blue Origin wanted. Within hours of the live stream ending, social media erupted with conspiracy theories. People claimed the flight was faked. They analyzed every frame. Hair in zero-G became a forensic battlefield. Does it float right? Why does it look stiff? The capsule hatch became another focal point. Wasn't that latch on the other side last time? Then came the really wild stuff. Claims of green screens. Allegations that hands looked like mannequin hands. Complaints about the lack of scorch marks on the capsule. Journalists methodically debunked the claims. Hair behaves weirdly in microgravity. The hatch mechanism is identical. Scorch marks aren't always visible. But the debunking didn't stop the theories. Now we have 2 flights, same rocket, 6 months apart. One generated a firestorm of attention and doubt. The other barely made a sound, and you have to ask, which is more suspicious? The universe keeps throwing us curveballs, objects that don't fit, signals that make no sense. And every single time, without fail, we do 2 things. First, we scramble to understand the science. Second, we project ourselves onto the mystery. Think about Oumuamua in 2017, the first interstellar object. It was accelerating. Something was pushing it. Scientists proposed outgassing, but a subset of people, including some scientists, proposed something else. What if Oumuamua was artificial? A light sail, a thin sheet of material being pushed by starlight. If it was artificial, maybe it was a probe from another civilization. The same thing happened with Tabby's star. A star showing bizarre dimming patterns, sometimes dipping by 20% or more. No planet could do that. Astronomers proposed dust clouds or debris, but one paper, half-jokingly, suggested an alien megastructure, a Dyson swarm of millions of solar panels collecting the star's energy. It sort of fit the data. Odd radio circles, fast radio bursts. 3. I divided by Atlas. Every mystery becomes a screen onto which we project our hopes and fears. Are we alone? Is the universe indifferent or intentional? The psychology here is powerful. Pareidolia, seeing patterns in randomness, is part of it. We are pattern recognition engines, and we're biased toward false positives. Better to mistake a shadow for a predator than a predator for a shadow. There's also existential longing. We want contact. We want to know we're not the only sparks of consciousness in a vast, cold universe. Every anomaly is a chance, a door that might open onto something extraordinary. 3I divided by Atlas is a mirror. In its glowing green coma, we see reflected our own curiosity, our hunger for meaning, our hope that the universe is stranger and more wondrous than we imagine. And maybe it is. Imagine the galaxy as a library. Not a library of books, but a library of objects. Comets, asteroids, rogue planets, ejected from the chaotic formation of planetary systems and flung into interstellar space. Each object is a message in a bottle, carrying information about the star system where it was born. And occasionally, one of those bottles washes up on our shore. That's what interstellar objects are, postcards from alien systems. Not alien in the sense of extraterrestrial intelligence, but alien in the sense of foreign, different, formed under conditions unlike our solar systems. And so far, every postcard we've seen has been different. Oumuamua. Dry, non-outgassing, strangely shaped, accelerating mysteriously. It didn't look like our comets. 2. I divided by Borisov. Rich in carbon monoxide. Fairly typical behavior, but with a gas-to-dust ratio suggesting a colder formation. It looked familiar, but subtly off. And 3I divided by Atlas. Gushing water and carbon dioxide at impossible distances, nickel without iron, cyanide appearing late. Nothing about its behavior fits our experience. 3 objects, 3 wildly different chemistries. If we extrapolate, if we assume these 3 are representative, then the diversity of comets in the galaxy is staggering. Not all planetary systems produce comets like ours. Maybe most don't. Think about that. In some systems, comets might be dominated by nitrogen ice, like Pluto's surface. In others, methane might be the primary volatile. And if life requires certain chemical building blocks, water, organics, phosphorus, nitrogen, then comets lacking those ingredients are sterile. But if even a fraction of comets carry the right chemistry, that fraction is important, because comets are galactic wanderers. They travel between stars. And if they carry organic molecules, amino acids, maybe even dormant microbes shielded deep inside, then life's building blocks can spread across the galaxy. This is the panspermia hypothesis. It's controversial, it's unproven, but it's not impossible. And 3, I divided by Atlas, with its water, organics, and cyanide, has the ingredients. Not life, probably, but the chemistry that could lead to life if delivered to a suitable planet. Now, let's return to that nickel anomaly. It's not just a curiosity, it's a chemical fingerprint. And fingerprints tell you where someone's been. Stars are factories. They build heavy elements. When massive stars explode as supernovae, they create nickel and iron. But not all stars have the same recipe. Young stars, formed recently, have high metallicity. Old stars, formed when the galaxy was young, have low metallicity. We think 3I divided by Atlas might come from the thick disk of the galaxy, an older stellar population. If the nickel decoupling we're seeing reflects its parent star's composition, then that comet is a tracer. It's telling us about galactic chemical evolution in ways we can't easily access. because we are holding a piece of a star system that might be billions of years old and thousands of light years away. We are reading history written in atoms. Now, let's try a fringe idea, one that most scientists would dismiss. Could anomalous metals like high nickel be signatures of processed material? Not natural, but technological? If an advanced civilization were mining asteroids, refining metals, building structures in space, they'd generate waste. That material would have unusual elemental ratios because industrial processes are selective. If a comet formed in a debris disk that contained industrial waste, it might incorporate those anomalous metals. To be absolutely clear, there is no evidence that 3I divided by Atlas is artificial or contaminated by techno-signatures. None. The idea is science fiction. The most likely explanation is mundane chemistry, just chemistry we haven't seen before. But the exciting part is this. Every comet carries a chemical signature, a barcode written in elements. If we build a library of those signatures, we can start to map the galaxy. 3I divided by Atlas is the first entry in that library. 3 objects. Oumuamua, 2I divided by Borisov, 3I divided by Atlas. 3 confirmed interstellar visitors in the span of 7 years. That's not many, but it's enough to do statistics. Enough to estimate how many more are out there, passing through undetected. Astronomers have run the numbers. They estimate that at any given moment, there are probably several interstellar objects within Jupiter's orbit. Small, dark, moving fast, invisible to most telescopes. We've detected 3 because we got lucky. How many do we miss? Hundreds? Thousands? Detection is hard, but it's getting easier. New surveys are coming online with unprecedented sensitivity and sky coverage. The Vera Rubin Observatory, currently under construction in Chile, will scan the entire visible sky every few nights. It's estimated Rubin could detect 1 interstellar object per month, maybe more. In a decade, we'd have over 100 confirmed interstellar visitors. That's a statistical sample. That's enough to start drawing real conclusions. But detection is one thing, studying is another. Interstellar objects move fast. By the time we spot them, analyze their orbits, and plan follow-up observations, they're often already leaving. Oumuamua was. We got one good look, and then it faded into the distance. Unless we intercept it. There are proposals for interstellar object intercept missions. Spacecraft designed to launch quickly, accelerate hard, and rendezvous with an interstellar visitor while it's still in the inner solar system. The technological challenges are enormous, but the scientific payoff would be extraordinary. Imagine landing on an interstellar comet, drilling into its surface, collecting ice and rock from another star system, and bringing it back to Earth for analysis in our labs. We could analyze precise isotopic ratios. We could analyze complex organic molecules. We could search for amino acids, for prebiotic chemistry. 3I divided by Atlas is a preview, a glimpse of what's possible. It's showing us that interstellar comets aren't just rare, they're everywhere, and they are carrying information we desperately want. That unseen population is out there, tumbling through the dark, waiting for us to find them, and we will. Now, let's zoom out. Let's look at the bigger picture. 3I divided by Atlas isn't the only weird thing happening in astronomy right now. Odd radio circles, ORCs, origin unknown, fast radio bursts, FRBs, mechanism debated, Tabby's star, bizarre dimming patterns, not fully explained. Oumuamua, interstellar object with anomalous acceleration, 3I divided by Atlas. Comet with impossible water production and metal anomalies, and those are just the high-profile cases. Astronomy is awash in things that don't make sense, and that's new. For most of the 20th century, astronomy was data-starved. You pointed a telescope at something and spent months analyzing it. Discoveries were rare. Anomalies were rarer. Now we are drowning in data. Automated surveys generate terabytes every night. We're detecting more stuff than we can possibly follow up on, and with high volume comes high anomaly rates. If you look at 1 billion objects, even if only 1 in 1 million is weird, that's 1,000 anomalies. We are in an era where anomalies outpace theory. We are finding things faster than we can explain them. This is both exciting and dangerous. Exciting because new phenomena drive new physics. The discovery of pulsars, of gamma-ray bursts, of gravitational waves, all started with unexplained observations. Anomalies are where breakthroughs happen, but dangerous because hype cycles can spin out of control. Every anomaly gets hyped as revolutionary, alien megastructure, warp drive signatures. The media loves it, the public loves it. And then, 9 times out of 10, the anomaly gets explained by something mundane. Dust, instrumental noise, a misidentified known object. The danger is credibility erosion. People hear maybe aliens 12 times and actually just dust 12 times, and they stop trusting scientists. Tabby's star is the cautionary tale. When the alien megastructure hypothesis made headlines, the public latched on. And when follow-up observations showed wavelength-dependent dimming indicating dust, not solid structures, there was backlash. But the thing is, Tabby's star is still interesting. The dust explanation doesn't fully account for all the observations. It's a weird star. It's still science, still valuable, just not aliens. The lesson is that anomalies are opportunities. They push us to refine models, to consider new mechanisms, to challenge assumptions. Oumuamua, even if it's just outgassing, forced Comet scientists to think harder about sublimation at low temperatures and exotic ices. That's progress. 3I divided by Atlas is another opportunity. When you stack enough anomalies, patterns can emerge. Maybe they're all related, or maybe not. The key is maintaining skepticism and wonder simultaneously. You can be excited about an anomaly without claiming it rewrites physics. You can change your mind when new evidence arrives. This is where good science communication matters. When reporting on 3I divided by Atlas, responsible journalists and scientists should say, "This comet is behaving unusually. We are investigating several possible explanations. Here is what we know so far." Not, "Alien comet violates laws of physics," but "Nuance doesn't generate clicks. Careful language doesn't go viral." And so the hype machine grinds on, turning every anomaly into a potential revolution and setting up disappointment when the mundane explanation arrives. The solution is to be honest about uncertainty. 3I divided by Atlas is one anomaly in a stack. It's important, it's fascinating, but it's not proof of anything yet. It's a data point, a mystery, an opportunity to learn, and the process of studying it, of testing hypotheses, of ruling out explanations, that process is valuable, that process is science. And so, here we are. We've walked through the mystery of 3I divided by Atlas, an interstellar comet pouring water into space where water shouldn't flow, glowing green with nickel and cyanide, switching on, like something deliberate, carrying chemistry from another star system, perhaps from another era of the galaxy's history. So, is it alive? In the poetic sense, maybe. It's dynamic, changing, responding to its environment. It's active when it should be dormant. It behaves in ways that feel purposeful, even though we know they're driven by physics and chemistry, not intention. But alive in the literal sense? Almost certainly not. There's no evidence of biology here. No metabolism, no reproduction, no information storage. 3I divided by Atlas is a rock covered in ice, heated by sunlight, releasing gas and dust according to physical laws. It's just that those physical laws are producing something we've never seen before. The most likely explanation is that 3I divided by Atlas is a natural comet, but formed under conditions very different from our solar system. Maybe it formed in a colder region where carbon dioxide ice is more abundant than water. Maybe its parent star had an unusual chemical composition, leading to weird metal ratios. The thick disk origin is compelling. If 3I divided by Atlas is 7 billion years old, if it carries isotopic signatures from an earlier era of galactic chemistry, that would explain the oddities. Ancient ice, ancient chemistry, ancient minerals, all preserved in the deep freeze and now being revealed. Could it be artificial? A probe? A derelict spacecraft? The evidence doesn't support that. Nothing about 3I divided by Atlas requires a technological explanation. Everything we're seeing can, at least potentially, be explained by natural processes. But maybe that's the real value here. Not whether 3I divided by Atlas is natural or artificial. Not whether its chemistry is merely unusual or genuinely revolutionary. But that it makes us think. It makes us question our assumptions. It reminds us that the universe is bigger and stranger than our little corner of it. That nature has had billions of years and trillions of star systems to explore chemical space. And we have barely begun to survey what's possible. Every interstellar visitor is a challenge. It challenges our models, our theories, our sense of what is normal, and challenges are how we grow. The next steps are clear. Watch 3. I, divided by Atlas, as it approaches the Sunday measure, everything. Spectra, light curves, gas production rates, and prepare for the next interstellar visitor, because there will be another and another. The galaxy is full of these wanderers, and our detection technology gets better every year. Each one will be a new puzzle, a new set of clues, a new window into how planetary systems form and evolve. Maybe one day we'll intercept one. We'll land on it, drill into it, bring back samples. We'll analyze its isotopes in terrestrial labs, study its minerals under electron microscopes. Until then, we watch, we measure, we wonder, because that's what humans do. We look up at the universe and we ask questions. Why is that comet active so far from the sun? Where did it come from? What can it teach us? The questions themselves are valuable even before we have the answers, because questions are how exploration begins. 3. I divided by Atlas came from somewhere out there, across light years and billions of years, carrying a message written in water, nickel, and cyanide. We didn't ask for this message. We don't know what it says yet, but we are listening, we are watching, we are learning, and in that act of learning, in that stubborn insistence on understanding, we find something that might be the closest thing to alive in this whole story. Not the comet. Us, curious, wondering, reaching out to touch something that came from an impossible distance, trying to read a letter from another world. The universe keeps sending these letters. Cosmic postcards, messages in bottles, visitors from the dark. And every time one arrives, we're reminded that we live in a vast, ancient, incomprehensibly rich cosmos. A cosmos that will forever outpace our understanding, forever surprise us, forever offer new mysteries. 3. I divided by Atlas is one mystery, one comet in an infinite sky. But now, it's our mystery. And whether it's just a chunk of ancient ice or something more, we will keep looking. We will keep asking. We will keep listening for what the universe is trying to tell us, because that's what it means to be human. To see something strange in the night sky and refuse to look away.